Hey guys, welcome back to day two of simple harmonic motion. And right after yesterday's introduction, a lot of people asked me a lot of doubts whether this thing, double pendulum, is it a simple harmonic motion? A simple harmonic motion has to go in a straight lane. Yes, it has to go in a straight lane. I've already also mentioned a pendulum is not exactly an SHM. If the pendulum's oscillations are like very, very small, only in the case when the oscillations are very small, then only you can consider it as SHM. The thing that you're looking at right now, it's called as a double pendulum, and it's definitely not an SHM. Okay, it's a complicated motion. It's quite a complicated motion. We don't have this thing in our syllabus, so we don't discuss that at all. Let's just get back to our job, our level standards. Okay, let's not fly. Yesterday I talked about oscillations, restoring forces, how the restoring force should always oppose the displacement and all. We've talked about it. Then I introduced that to the idea of a mean position, a positive extreme, a negative extreme, plus a minus a. And then the idea of time period, what exactly is a time period, how to understand a time period. And I mentioned that we are going to talk about the mathematics of yesterday was just understanding, more of an understanding what an oscillation is, and then what is a periodic function is, what is a combination of an oscillatory periodic motion is, and then in that oscillatory periodic motions, the simple harmonic motion is a very special case where the force is proportional to minus x. This minus indicates it's a restoring force, and we put a constant there, and x is a displacement, so we always have a restoring force that is proportional to x. So this is a very special case, and we call this as a simple harmonic motion. Or you can introduce a simple harmonic motion like this also, where acceleration is proportional to minus x, where again the minus represents it's a restoring acceleration. Okay, so today let me introduce to the same idea, acceleration proportional to minus x, but to put it, people put a omega square there to write in a to write it in an equation. We can't simply then what do you call it as fixate on wait a second, yeah, you can't just leave the equation on the proportionality. You have to put some constant, so that is why I introduced a constant which is omega square. But it is strange that you randomly put a square constant there. Like, why should I put a square constant? Aniket, what is it?
Sir, so that it's always positive.
Yeah, that's a way to put it. Like, yeah, I can simply say that some constant, and the constant is also positive. I can simply say that also, right? Like yesterday, I when I talked, we can write f equals to minus kx, where k must be a positive constant. I can simply say this, but why do I have to bring a new value omega and put it as omega square? Okay, you getting my point, Aniket? You're getting my
Yes,
point.
sir.
Yeah. Why do I have to call it as omega square? And it's not just that. In the later classes, we are going to call this omega as something called angular frequency. Where did that even come from, like out of nowhere? What is this angular frequency, and why did I put it there? Sadly, this is how most of the books actually introduce you to this topic. They simply say acceleration equals to minus omega square x. This is called SHM. Not the greatest way to put it, like, because I don't really like it that way, like making you understand. The way I want you to understand, f proportional to minus x, or acceleration proportional to minus x. And if you want to put a constant, yes, you can put a constant here also. Yes, you can put a constant, but they put a omega square. You will understand why there is an omega square here later. That is why I'm not really asking you to just have it there. We will understand why there is omega square later in our further topics. Aditya, what is it?
So is this omega equal to root over k by m?
Obviously, like when you write the same thing, f equals to minus kx here, we already put a equals to minus omega square x. So let's do that. Ma equals to minus kx, a equals to minus k by m x. So a equals to minus omega square x. We already have this thing as a definition. We don't know
Yes,
where
sir.
it came from. It's just a definition. Like this is acceptable. Writing x acceleration proportional to minus x is an acceptable thing. For writing force proportional to minus x is an acceptable thing. But this omega square, we don't know where it came from. But looking at the equations, yes, it looks like omega square equals to k by m, and that is leading to omega as root over k by m. Again, in yesterday's class, I kind of mentioned this ratio. This ratio of k by m is going to make a lot of sense. Do you, any of you remember? Aditya, do you remember?
Yes, sir. You told last time that we
Like,
will study
what were
this.
the words that I used here? K and m. There were some words that I used to describe these two things.
The M
Sir,
was
inertia.
inertia, sir.
M is
M,
inertia, yes.
K is like the strength, sir.
Now, what
You
strength?
told
I used a
like
specific
this
The restoring
restoring force
force.
strength
the restoring capability. Yes.
capability. Yes.
Yeah. So the K is representing the restoring capability, and M is representing the mass. Sorry, the inertia of the system. So this omega, the angle, we don't know it yet. We didn't define it yet as angular frequency, but this strange term right here is coming up as root over k by m. This is how the strange definition actually comes in most of your books. They randomly put it here onto your face. But I want you to just remember this idea that yeah, there is a term called omega square which is mentioned as a positive value, and when we checked it, that omega value is coming as root over k by m. But what exactly does this all mean? We will slowly look into it, slowly get into the topic and try to understand. Let us start with our basic knowledge only. Okay, there are 8 people in the waiting room. Let's check if I know any
Excuse
of
me, sir,
them.
one small doubt.
Yeah,
So that omega square or that k can be some variable.
the omega square are
K can be some variable, sir.
variable as in
Like there can be some variable y dependent on something, something like that.
no. For a specific material, it has to be constant.
Okay, sir.
Like if you take a specific spring, the k must be constant. That is why it's called a spring constant.
Oh, okay, sir.
Okay, right. So yeah. So I was saying something. Yeah. Let us get to the basics. Let's just imagine we don't know that what that omega is. All we still know is the acceleration is proportional to minus x, force is proportional to minus x, and we all we know is basic equations only. F equals to minus kx only. Our acceleration is proportional to minus k by mx. Or let's just be a little moderate and accept this term omega square term here. Let's just accept it and go forward. Let's see what happens. Okay, so this is a oscillation. This is a space where the oscillation is taking place. There is a mean position, there is an extreme, a positive extreme and a negative extreme. And there are two ways here. Like we can go a really long path saying I only know the velocity at some point x naught as v naught. Let's just say we already know these velocities, and some other point x we don't know the velocity v. So in between these 2 points, I want all the things that are happening, all the kinematics equations, what the thing, the way the things are happening. Again, our original style, like acceleration equals to minus omega square x. I can write acceleration as what can we write it as? M into, sorry, not, there is no m. We can write acceleration as dv by dt into omega square x. This is a difficult path I'm taking. Okay, like I said, like in the beginning of the class, there are two ways to look at this problem. Once we look at this, we'll go back to that problem and look at it, which gets really simple. Okay, trust me. The other process, the other path is really simple. We will look at that path right after this thing. So dv by dt. Now I can write it as dv by dt, but there are three variables now: the velocity, the time, and x. All the three variables are three things are variables. Now I don't want to do that. Instead of this, I would write acceleration as dv by dx into dx by dt. Oh, wait a second. Yeah, we can write it that way. It's like I multiply dx, so I write dv by dx and dx by dt. There is a reason why I do that. Don't worry yet. Now dv by dx is nothing but dv by dx, but dx by dt is nothing but v. The reason why I did this is I bring this whole thing into only two variables. There is only velocity and x now. There is only velocity and x. So I take the advantage of the situation saying uh, v dv, I leave it on this side, minus omega square x dx. I send the dx to the other side, x dx. Now I integrate. Where do I'm leaving omega square out since it's a constant, like I just mentioned. Now, when we put the integral limits, what do we need to put it as? Where did we start? We started at some x naught displacement, went to x. Started it with v naught velocity, went to speed v. So v naught to v, x naught to x, v naught to v, x naught to x. We integrate this thing, you will get some really big terms. I don't want to waste the time. I don't want to waste the time in the class right now. The things, Aniket, you're saying something in the text again. Please raise your hand and say. I'll just show it to you in that HCFM already. Like they do this thing, like, yeah, integral v naught to v, v dv, integral x dx, x naught to x. They put the limits and they get here. They slowly integrate and look how they got. All these steps are basic integration only to this point. Clearly observe, guys. A lot of steps here that we make, they don't truly make sense. It's not something that is intuitive that you can do it. It's as if somebody knows where they're going, somebody knows what they want from this equation and trying to get that. So I don't really find this intuitive. Like it's not as if I write this equation, what do I do from this point? I just want to leave it like this. I have a relation between v and x, and then let's just call it that. But they don't want to leave it that way. They want to call this as a, this whole term as a. Now what happened? Velocity equals to omega into this. So guys, this is the equation, something that they already know. They want to bring this. Let's just say, let us just put it that way. Okay. I don't really find it that intuitive, but the idea is they just found a relation between the speed of a particle to its displacement to any point, at any point, the speed of a particle and its displacement. So let's look at these equations first. Let's look at this specific equation first. Let's observe that. Where did we get, what did we get at the end of this whole thing? We got v equals to omega into root over some a is a constant. That a is again amplitude. We'll get to that point why we got that. But let's just accept this equation again. Okay, like, yeah, it's as if they know this equation and try to bring the whole thing to this point. That is why I don't really find this that intuitive. Can somebody tell me why, how he got it? How did he mention this?
Sir, I have a different method of seeing this equation, sir. Can I say
Yeah,
once?
we definitely will get to a point
Sir,
where
can
we
you
have
get back to that diagram, sir? What you made?
which diagram?
In the notepad you made
Yeah,
once.
yeah.
Yes, sir. A bit.
Yeah.
Yes, sir.
Hmm.
So instead of taking v naught and x naught, sir.
Mhm.
Yesterday while discussion, you once said like this at this amplitude it should be zero so that it should come back, na sir.
That is a good way. That's a very
So
good way
like
to put
I'll
it.
take the amplitude and say velocity is zero, sir.
Very
So
good. Excellent. Yeah.
at x naught I will say zero, and that instead of
So
like
that will
this,
change all the limits. I can
yeah,
say
change limit, sir.
this thing is zero, this thing is V max.
No, no,
The other thing, the other way to put it, the other way to put it, like Aniket, sorry, Aditya is saying, he says the initial point, let's call it as amplitude itself. At amplitude, the velocity, the speed is actually zero. That's what we've already practically approached to this point.
yes, sir.
From the
Then
mean
we do
position
then
at the
it
extreme position, the speed is zero. It's something that we already know, right? So he's asking us to use that idea and approach, come to this equation. Like if you put these values, you'll directly get to this equation only. But in the
yes, sir.
textbook, he took a long path, and when he mentioned this equation, do you know how he got there?
Nah.
It's basically conservation of energy. There are 2 points in between in between the 2 points that we know. He simply wrote the energy conservation at these points and he got that thing. That's all. Like he wrote the energy here and he wrote the energy at the extreme position, half kx square And at this position, half k x naught square plus half mv square. So he equated these two things and got the value. That is why I'm not really satisfied with this approach. It's as if he knows what he wants to get, and he got there. Okay, using all the trigonometrical equations, he got it there. So that is why let us not look very deep into the process that we just followed. I hope you get the process that they just discussed, but let's not break our heads, try to understand how we got there. There is much easier way, a lot more easier way to do this. We will do this right after this discussion. But look at this equation. Let's look at the equation saying speed some omega. We don't know what this omega is yet. We don't really know what it means. Amplitude and x as if from the mean position, this is a positive extreme, this is a negative extreme, I can go to any point. Let us say I can go to a point of a by 2 and ask the speed at this point. How? V at x equal to a by 2. How do I find, Aditya? I want to find the
So
speed at this point.
we have to substitute this a by 2
Exactly. I
in
will
place of
simply
x, sir.
substitute root over a minus a square. In the
But
place of
one
x,
sir
I
doubt.
simply put a by 2 whole square. I'll get the value as omega into root over a square minus a square by 4. I'll get root over root 3a by 4. So this is the answer.
Sir, I have one doubt, sir.
Yeah.
So let's imagine like it will go there, then it has to come back to that point. So it will have the same velocity.
Not exactly. We're not talking about velocity, we're talking about speeds. I'm glad that you asked the same question. Mean plus x minus, sorry, plus a minus a, it went there with a velocity. When it come back, when it comes back, it will have the same speed but is in the opposite direction. That's all.
Okay.
Okay.
So
So you can find at any point, like you can put the value of x, like why not put x equals to minus a by 2? X equals to minus a by 2. I'm writing the equation v equals to, guys, try to remember this equation. This is an important one. I know it's not the most intuitive method to get here, but try to remember this equation. This is important. Once you get the easier method, you will thank me for doing this. Okay. So instead of x equal to a by 2, put minus a by 2. What do you get, Aditya?
he will get like a phi a by, like
You
it
are
will come.
stupid as a rock. Like take a small pebble. The amount of IQ that pebble has, you also have the same amount. Okay. How is
Huh?
it different? It's exactly the same thing. It's there is a square.
Yes, yes.
So you will
I do the minus out. Wow.
do you agree that you have an IQ of a pebble, a rock, a little?
Sometimes.
Yeah, sometimes.
Sometimes.
So you're getting the same value. So you're clearly getting the same speed on this side also, but the directions are different maybe. So like try to look at this whole thing in an intuitive manner only for now. Mean plus a minus a, you go to any point, you get some speed. Let us say I go to a by 3. Now, when the body is going at a by 3, it has some speed. Let us say, let's call it as v1. I'm pretty sure when it is coming back to the same point, it will have the same v1 in the opposite direction. And on the other side at a by 3, it will have the same speed in this direction, v1 only. It goes back and by the same point, it has the same speed, v1 only. That is the important point. So it's as if the whole thing, the speeds are completely mirrored on this side and this side. At any point, you have some speed, you want the same speed on the other side. Yes, yeah, the directions could be different depending on the time whether it is going away or coming back. Whether it's going away or coming back, the timings could be different. But at a specific point, yes, the distances are equal. So that is why to find the speed at any point, you have this equation omega equals to root over a square omega into, sorry, v equals to omega into root over a square minus x square. That is why this thing is so important. Do you get it?
Yes,
Aniket.
sir.
Aniket.
So once again, can you explain how we got that A from those big equations? That's a bit tough to understand.
Which part?
So in the HCV which they gave and then gave it as A.
Yeah. like in this thing, this whole thing is mentioned as
Yes,
A,
sir.
right? Yeah. This whole thing is mentioned as simply A. What I'm asking you to do, like he actually did that. It is so stupid to write about the energies right away. Uh, he kind of did it here. Look at this part. He talked about energies, potential energies, kinetic energies. So he kind of got it. Ah, come on, we went to some other topic. Where are we? Hmm. So he kind of talked about the energies right there itself, and okay, he didn't even mention here that the energy. Why I write it as A? Forget it. But I can tell you why it is, because like take this file, take this specific thing. Remember when you write the energies in the entire SHM, he's talking about at this specific point energy, kinetic energy and potential energy as half mv naught square plus half k x naught square. At the extreme, the energy is simply half ka square because there is only potential energy, there is no kinetic energy at the extreme. He's simply equating these values, and from that, you will get this equation. Aniket, do you accept it? Or is it too much to accept?
Sir, that whole thing, how is it equal to, like, it's not equal to A rate, sir. It's equal to A square.
What?
He wrote A square only there.
A square only. There is only a square.
Sir, you said A, sir.
There is a square
My
only.
God.
So we have to try
Got
it once
confused
on our
then.
own to understand this.
Yes, sir, I
Yes, I
didn't get this
agree. I
whole
agree.
thing.
Guys, please, if you want to understand the difficult method, please go ahead and try this.
Sir, that omega feels like it's angular velocity, sir. Like V is equal to R omega. It just feels like that for a second.
It's a very good idea that you came up with this idea. It is actually an angular velocity. That is what you're going to see in the next easier method that I'm going to give you. Okay, but who is going with an angular velocity here?
I got the same note, sir. Like, how can
Yeah,
we
who is
equate
no
it?
nobody's going with an angular velocity here. But where did the angular velocity come from?
So maybe from angular momentum. Like for angular momentum, there's no need for angular
No, no, we
velocity.
will talk about it. Guys, please, if you are confused by this moment, please completely ignore what we just did, the whole thing. Okay. He did a lot of things to bring answers, to bring this specific answer as v equals to omega into root or a square minus x square. Okay. This is what he was trying to do. We will get this thing in an easier method for sure. You will thank me, but please try to accept this fact that this is the equation that we're getting. Now using this idea, you should be ready to give me the values. Like let's do some problems using this idea, because if I give you the method, I always do this thing, you people know, if I give you the easy method right away, you won't even look into this method, which is a bad thing. Sometimes there could be some problems where you need to use some ideas from this method. So that is why I'm stressing you on this thing. Let us look at this thing again. Mean position extreme, so plus a minus a. Let us talk about the speed at the extreme. Let us put x equal to a only in the place x equal to a. What do I get? V equals to omega into root or a square minus a square. What am I getting? The speed as
Zero,
zero.
sir.
Yeah, the speed as zero. Let Aditya speak. If I put x equals to minus a, what do you get, Aditya?
So zero only, sir. This time I won't make that mistake
Yeah,
again.
so it is again zero, even though you have a minus, you square it, so it is zero. Let us talk about the mean position. So V equals to omega root or a square minus what is x here?
Zero, sir.
Zero, sir.
Zero. So you're getting a omega.
Omega is, sir.
So remember this value also. This is called as a V max. Sorry, why did I put it as zero? I'm sorry. V max equals to a omega for an SHM.
Oh.
For an SHM, the maximum speed always occurs at the mean position and the value is a omega. At the extremes, V is zero. At the negative extreme, V is zero. And at any point, you can find its speed. You can, at any point, I give you the x value, x equals to some 5a by 6, let us say. I want the speed at this point, I simply put it in the equation. V equals to omega root over a square minus 5a by 6 whole square. Find the value. Is my voice too low? Somebody is complaining.
Yes, sir. Like suddenly decrease, but
I'm
Yes.
sorry about it. Maybe I was sitting way too far from the mic.
Sir,
So,
now it's too loud, sir.
oh, I can't do anything about it. So, yeah. Aniket, what is it?
So you can keep your voice loud. We'll reduce our volume.
Yeah. You do whatever
That's the
you
best
want.
thing we can do.
Yeah, you do whatever you want. So what I'm trying to say is, like, you understood this level, right? Like, we have a hope of relating the speed of the particle at any point with the displacement of the particle at any point. Now what we're going to do is, oh guys, it's not just the speed, we also have the acceleration also. If you remember, speed is written as b equals to omega root over a square is x square. Acceleration is also in the place of x. So whenever I give you any position in between plus a and minus a, you should be able to write the speed and the acceleration also.
This one's like the angular acceleration formula, right, sir?
No. Don't bring the angular things right now into this thing. This is just a linear acceleration, the linear speed of a particle. You should be able to write. Let me just give you some positions. Okay, x equals to a by 4, x equals to
Your screen pause, I think.
no, it didn't. It's writing x equals to 3a by 4, and x equals to minus what do I write, minus 3a by 5. I want the speeds and accelerations at these specific points. Can you people tell me all the values, please?
Yes, sir.
Yeah. Be quick and give me the speeds and accelerations. Let us take the first question as x equals to 3a by 4. The second problem is x equals to a by 4. The third problem is x equals to, what was the third thing? Minus 3a by 5.
So omega value will be given in question.
If they don't give it, yeah, they have to give the omega value. If they don't give it, you'll have to calculate it eventually. You'll learn it. Okay.
Okay, sir.
So let's talk about them. X equals to 3a by 4. So speed v equals to omega into root
So
of
root over 7a
a
omega by
square
4, sir.
minus 3a by 4 whole square. So you get our very strange value, I guess. Omega equals to a square minus 9a square by 16. So you get omega into root over
7a by 4,
7a
sir.
by 4, sir.
7a square by 16. Yeah, let's just leave it all, the whole thing in the root itself. So that is v. And if I have to find the acceleration equals to minus omega square into 3a by 4. That's it. Agree?
Yes, sir.
Yes, sir.
Right. So similarly, I have to do the same thing for a.
15 by 16, sir.
I don't care. It's a positive thing again, so I don't have to calculate it. Let us do the first negative value. Minus 3a by 6. Did I give 3a by 6 or 3a by 5?
It's 5, sir.
It was 3a by 5. I'm sorry. So let us write it as 3a by 5. So minus 3a by
16
5.
by 25, sir.
So omega, you're good with calculations. Minus 9a square by 25. So you get root over 16
Sir, it's 4 omega by
square
5,
by
sir.
25. And again, acceleration, if I want, I put minus omega square into minus 3a by 5. So you'll get a positive acceleration here. Omega square 3a by 5, which means the acceleration is in a positive direction in this case. I hope you're getting it. The acceleration is in this direction.
Yes, sir.
Okay.
So one doubt.
Yeah.
From these two equations, can we get the time also, sir?
Absolutely, yes. Shall we do that?
Yes, sir. Sir, and can we apply those 3 laws of kinematics?
No, not at all. Why not? Why shouldn't you apply the new 3 laws of kinematics? You should not, guys. At any cost, if I find any of you people using v equals to u plus at, or v square minus u equals 2as, or s equals to ut plus half at square in this topic, I will find you and I will kill you. Have you seen the movie Taken? It's like the
Yes,
same warning I'm
Mostly.
giving you. Okay, why shouldn't you use these equations again?
so because acceleration is changing.
Sir, because
Exactly,
acceleration
the
is not
Because
acceleration
constant.
is
acceleration is
not
changing.
constant, so you should not use these equations. Okay,
We'll have to use the differential equations, right? Sir?
you have to use the differential equation only. Otherwise, you can simply use these two
We
terms.
can use these
Like,
equations.
these two
These are
terms are
better.
like always available for you. So at any point you want to find the velocity, you want to find the acceleration, you can happily use them. uh like Aniket said, he wants to find the time. Let's do that. Okay, before doing that, let's just give it another conclusion, a final conclusion, a final understanding conclusion, seeing at mean, a positive extreme, negative extreme, v max in this direction, which is a omega, goes to this point, becomes zero, and when it returns, it again is v max. So v max is minus a omega, since it's in the opposite direction, goes to the negative extreme, v becomes zero, and it comes back to v max. That is the story of velocity. Let us talk about accelerations. At this point, acceleration is zero. Do you all people agree? Because acceleration equals to omega square x. Since x is zero, so acceleration is zero here. At this extreme point, acceleration is a max. At this extreme position, acceleration is a max. It's a simple thing. Acceleration is a max and acceleration is a max. If you want that value, yes, you can write minus omega square a. Since it is in the opposite direction, that is why there is a minus. Here, minus omega square of minus a, so that is omega square a. So this is a maximum acceleration value. This is a maximum speed value. I'm sorry you are doing it all without a complete understanding, but that is the way you should be doing the, like, sometimes you just have to go with this flow, kind of a flow. Okay, I hope you understand the story of speeds and accelerations. Once you get the story of speeds and acceleration clearly, out of Aniket's request, let us go hunt for the time. We have an equation saying omega equals to root over a square minus x square. Yeah, it's the hard way. Now I'm going to write v as dx by dt, omega into root over. So Aniket is going to help me on this thing. Aniket, can you raise your hand and follow me with the steps?
Yes, sir.
So dx by root over a square minus x square omega dt. I only see two terms now, x and t. I happily can integrate. Please, Aniket, how do you integrate on the left side? What is the term that you get?
I have to do it, sir.
You said you'd help.
So integration freaks me out.
No. So what's the integration? What's the integral term for this?
Minus 1 by a square plus x square.
Shut up. Anyone else?
So it should be like in the denominator side, a square minus x square whole power to 3 by 2, sir.
Guys, shut up. You either get a sine term or a cos term. You people don't even remember these values. What's the differentiation of sine x? Not sine
Cos
x.
x, sir.
Oh, wait a second. You don't get a sine term. You actually get a sine inverse and a cos inverse terms.
Oh, yes, sir. Now I remember.
Do you remember the differentiation of sine inverse x? It is around 1 by root over minus 1 by x square. So the integration of this thing is becoming this. So the
Then it would
integration of a square minus x square gives us something like 1 by a sine inverse x or something like that, I guess. Let's look at that. That is also here. Yeah, right here it is. So what he does is he does the same integration. He gets a sine inverse x. In the end, the important thing is he comes up with this point. Aniket, as you asked, we have the displacement and time linked clearly. Displacement
Okay,
and
sir.
time. Okay. Again, it is as if somebody knows that this is the equation that we need to get. So we do all the method to get to this point. Okay. It's not completely a fair thing to look at. But guys, again, like what we did is simple
So what is
integration.
delta?
Yeah. Delta. We will talk
So
about
what is the delta in the
the delta is a villain for our life. Let's talk about this delta. Let's just imagine for now the delta is zero itself. Okay. The delta is zero for now. Don't have to worry about it. but we have to worry about this equation. No, don't have to worry. It's like this is the important thing again. Like just like v equals to omega into root or a square minus x square, we reached this equation using the hard way. But again, using the same hard way, we again reach to another equation saying x equals to a sine omega t plus delta. But let's just leave the delta for now.
Excuse me, sir.
Yeah.
Sir, like, will these derivations be any useful, like in some advanced and all?
Yes, they might be.
So we have to learn the hard way
It is
completely.
important, yeah. If you're
Okay,
talking
sir.
about an advanced exam, yes, those derivations are important. You're supposed to learn what you're doing, right?
Okay, sir.
So right after the first equation, v equals to omega into root over a square minus x square, and the other equation acceleration minus proportional to omega square x. We already know these equations. We reached the third important equation where the displacement is written as x equals to a sine omega t. Or there is a delta, but let's just call this delta 0. It doesn't really matter. It's not a big deal. Okay. So now we came to this equation also. Now we have the displacement of a particle in terms of a. Let us look at the nature of this equation also. We all know the value of sine varies from plus 8 plus 1 to minus 1. So which means this equation is clearly saying that the value of x will go to plus a and minus a. It will vary in between these 2 points only. That's what we know already, right? That is something that we already know. The value of x varies from plus a to minus a, and according to the time we are talking about, yes, now we can find the time also. Let us say somebody gave you a situation saying mean, positive extreme, negative extreme. Everyone knows that for the whole process it takes a time period of t. But what if somebody asks you, it started here, what is the time taken to get 2 plus a by 2 only? What is the time taken to go to plus a by 2? This is where our new equation is going to helpful. X equals to a sine omega t. I'm going to put x equals to plus a by 2, a sine omega t. Once I do this, what do I get? I find the time. Aniket, you have to stay right up because it's your uh, request.
Yes,
So
sir.
what is the time? How much is the time? Now, please tell me. I have to cancel these two, right? So I have 1 by 2 equals to sine omega t. Sine omega t is 1 by 2, which means omega t equals to,
Sine inverse 1 by 2.
how much is it?
Oh, okay, sir. 30.
What?
30 degrees, sir.
30 degrees or pi by 6. I can write it as pi by 6. So the time taken to get here is pi by 6 omega. They give you the value of omega. Still, we still don't know what is omega doing here. Like omega is a thing that we've learned as if it is a angular velocity. But why did it come here? Nobody knows. Let's look into it. Let's slowly get there. Okay. But the time for it to get to that point is this much. That's what we have here. So it is a easy way to do. So even though it's not just the entire motion, now I can find the time for the particle to get to some point. Or let us say I want the time for it to from here. This is called as 1. All the way it goes to a point where it is minus. Sorry, there is a minus. There should be minus on the other side, right? So all the way to minus a by minus 3a by 4. What is the time taken to travel to this point? You find to get to 1, you find the time to get to 2, you find the difference, you will get the time taken. But it still sounds so difficult. I mean, you still don't feel what you're doing, like why you're doing this all, right? So I'm going to introduce you to a lot more easier method, which puts all the things, all the confusing things that we just discussed this entire day into a simple idea. Before I do that, Aditya seems to have a doubt. Aditya, what is it?
So what is the time taking by 2 second time, sir?
Okay, Robo Man, I don't understand what you just said. Your voice is breaking.
Sir, now my voice is coming.
Yeah, it's better.
Sir, I am asking like what if it asks the time taken to pass A by 2 second time? Like first time it went like that, then
Yeah,
second time it
so
is.
yeah. Oh,
We'll do
that's a
two
good
times,
question.
sir.
That's a good question. That's a good question. So when you solve this thing, when you write sine theta equals to 1 by 2, you don't just put pi by 6, right? Pi by 6 is not the only place you get 1 by 2. Sine theta gets 1 by 2 multiple times. So I write sine omega
Yes,
t
sir.
equals to 1 by 2. If have to write omega t, I have to write pi by 6, which is 30 degrees. And then it comes the same point at 120 degrees, I guess. Is it 120 degrees?
Yes, sir.
No. It's not 120. It is, I know it
Yes,
is.
sir.
I know it is 150 degrees. And then it comes at 390 degrees, and then it comes at some other value. So all the values I write all the values at line. So this is the time taken for this angle. This is the point where it goes there by first time, second time, third time, fourth time. I just keep on writing all the values and you'll get all the times. Again, sounds like an exhausting process. I am exhausted. Are you people not exhausted with this process? I hate this.
Yes, sir. The omega
Sir,
is the biggest problem, sir.
instead of finding the multiple angles, sir, we can simply add t every time, right?
No, not T. No.
Sir, like this is some sort of uniform motion. Let's say simple
But
happen.
like you're talking about,
It keeps repeating, right, sir?
yeah. But the point is, like he's talking about plus A by 2. It, if you add T, you'll talk about this point. You're missing out this point. You see that?
Yes, sir.
So to
Understood.
find this point, you have to write all the angles. So you have to write 30 degrees, have to write 150 degrees, you have to write, guys, but stop it. Like I feel like I'm making you go through this hell intentionally. It's just, so stop with this thing. Okay. Let us just introduce
Sorry,
ourselves.
So
sir.
one small doubt.
Come on, what is it?
Sir, do we have a relation relating acceleration and time?
What? Yeah, yeah. You have x equals to a sine omega t, right?
Yes, sir.
So acceleration equals to minus omega square x, right?
Oh, okay, sir. It's a direct
I put the
relation.
x here. I have the equation for acceleration also.
Okay, sir.
Happy?
Yes, sir.
Do I have the equation for velocity time?
So it was there in HCV.
You are an idiot. Velocity equals to omega root over a square minus x square. I put this x, I have the equation in the terms of velocity also. Okay.
Okay, sir.
But
Looks
enough
very
of
easy.
this. Stop it. Shut up. Your time is up. You might have all seen that YouTube video that I've made, but now it makes more sense to you people about a thing called phase difference. I talked about it, but it wouldn't have made sense to you back then, but right now it does. Okay. I call this the mummy baby diagram just for fun. Let us just imagine there is this mummy going in a circular motion whose radius is a. Now, as the mummy is going in a circular motion, let us just imagine the baby is only allowed to travel on the y-axis. It is tagged to the mummy. It's as if it is a shadow of the mummy. Okay, it's like whenever the mummy is here, the baby wants to be here. So they both meet at here. They both meet at this point, obviously. And then when mummy goes to work again, the baby follows like this. And then mummy goes to this point. Oh, come on, wait a second. Mummy, baby can't go there. Yeah. So when the mummy is here, the baby is like here. Can you just run this whole simulation? Guys, can you run this simulation? You guys are on mute. So raise your hands. I want you to run this simulation as much as possible. Like whole mummy is going around this circular path. They simply use it as if this is going like this and the projection is going like this. If you clearly observe, we are going to do that. we are clearly going to do that, that this baby which is oscillating on y-axis is going to execute an SHM. Okay, now that thing is going to make us the whole process so simple. This whole thing or circular thing is going to make us the whole thing, which looks like a very easy thing, very easy thing. Okay, raise some hands before I
So
ask.
why do we do this in the first place? Like we already know what's a SHM
No,
and
you'll get it,
why do
you'll
we do
slowly get it,
this?
you will slowly understand it. Okay, the importance of mathematics, this is where it kicks in. Okay, this is the first point where maybe you see the importance of trigonometry. Until now you don't even know why you're using trigonometry. For the first time you might be looking at it, so try to understand this thing, guys. Don't look at the right side graph, just look at the spring block and the circular motion diagram. Look at how things are varying as it is moving. Okay, it's as if the baby is not written on y-axis, it is represented on the block itself. Okay, so as it is going, the spring block system is linked to it. Try to look at this diagram for a few minutes. I'm going to ask you some questions, you have to give me the answers. Okay, like I give you the position, you have to give me the baby position. I'll give you the baby position, I have to give you the mummy position. So you will go like that. Okay, like look at this animation for a while. Oh, it is done. Acha, there's a limited time it can only run. So you get a good grip of that thing. Once you get a good grip of it, let me start asking some questions. Let me give you some. First, I'll start with the baby positions. You have to give me the mummy positions. As if simply give me the quadrant, like which quadrant is the mummy in. Okay, I'm unmuting Aniket, Yashwant, Sumant, Aditya. Guys, are you ready?
Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
sir.
So just give me the quadrant number. Like I'll give you the baby position. You give me the mummy. Which quadrant is mummy in?
Okay, sir.
Yeah,
Q1, sir.
Q1.
first quadrant.
1 and 2, sir.
It's a
No, it
Q1
is
only,
just in the
sir.
first quadrant only. For now, it
Yes,
is
sir. It's
first quadrant. It
Q1,
is
sir.
going up. You see the direction also, so it is going up. So mummy
Okay.
has to be in the first quadrant.
Still in quadrant 1, sir. Second
Now,
position which
Okay,
you
like
have
that
told.
it's okay.
if I draw it like this,
Quadrant.
Quadrant 2, sir.
Second quadrant,
now
sir.
we are talking
Second
about
dog,
quadrant.
second, sir.
Good.
Sir, excuse me, sir.
Yeah.
So we can generalize it like if the baby is going up, mummy will be on the right side. If it's going down, left side.
Yeah, that's a good way to put it. Yes, so if it is the baby is going all the way up, mummy is like this. The baby is coming down, mummy is like this. Yes, but yeah, try to look at the quadrants quicker. Okay, let me draw more. Uh, are you ready?
Yes,
Yes.
sir.
Yes, sir.
So quadrant 4, sir.
Quadrant 4.
The
Quadrant
fourth.
4. Are you sure?
Yes, sir.
Yes, sir.
Yes, sir.
Uh,
Yes, sir.
3, sir.
Quadrant 3, sir.
Quadrant 3,
Three,
sir.
sir.
Quadrant 3.
Quadrant 3.
Quadrant 2, sir.
2,
2,
sir.
sir.
Quadrant 2.
Quadrant 2, sir.
Quadrant 1,
1.
sir.
Quadrant
sir.
1.
good.
Sir, it will be at,
He did not
On the
start.
x-axis.
he will,
On
he'll
the
be at
x-axis, yes.
positive
Yes, sir.
x-axis, sir.
That's a good way to put it. Yes, it is at the positive x-axis. If I take the same position, put it downwards, if it must
It will be
be,
in the negative
Negative
side.
x-axis, sir.
it will be a negative x-axis. Yes. Okay. Now, yeah, at these points they actually meet. So if I give it, the mummy is also there. If I give it here, the mummy is also there. Okay. Now, so guys, this is the thing that why don't we use it the other way around? I'm not even going to draw it. I'm not even going to draw it. I'll give you the mummy positions just by orally, like I'll give you the quadrant numbers maybe. You have to make a statement saying if it is in this space, like if it is going up in the positive x-axis, positive y-axis, going away from the origin. If it is like coming down in the positive y-axis, coming towards the mean position, like not origin, mean position, just call it as mean position. If it is going away like this, in the negative y-axis, going away from the mean position. If it is like this, in the negative y-axis, coming towards the mean position. This is how you put it. Okay, are you guys ready to do that?
So instead of mean, can we say going up and down?
No, don't simply say up and down. Like mention whether it is going away from the mean or towards the mean. That is a good thing to do.
Okay, sir.
Okay, because
Okay, sir.
sometimes SHMs are going to be like this. Sometimes SHMs are going to be like this. If you use the term up and down, it doesn't make sense anymore. But away from the mean, towards the mean, they always make sense, no matter where you're talking about. Okay.
Okay, sir.
Right. So let's use, let's say mummy is in second quadrant.
Sir,
Towards the mean,
towards the
Towards
mean, sir.
the
Towards
mean,
the
sir.
mean.
Towards the mean,
positive y.
Positive Y, sir.
positive y towards the mean.
Yes,
Mummy
sir.
is in third quadrant.
Away from the
Away-
mean,
Away
fourth
from the
quadrant.
mean, sir.
Away from the mean,
Fourth
third
quadrant,
quadrant.
I guess.
Away
Third
from the
quadrant,
mean,
sir.
negative y axis.
Negative Y axis, sir.
You get that?
Yes, sir.
Yes, sir.
Yes,
Right.
sir.
So this
Getting,
is how
sir.
you need to put. Let me take it a little further and try to give you the angles itself. Mummy is at 60 degrees.
Sir, quadrant 1, sir.
Quadrant
Moving away
one.
from the axis, quadrant, positive Y axis, quadrant 1, sir.
Exactly. Mummy is at 60 degrees, which means the baby is in positive y axis, moving away from the axis. Sorry, moving away from the mean position.
A by 2, sir.
225 degrees.
3 by 2, sir.
So
220.
it's in third
Quadrant.
quadrant.
Sir, away from the
So
away from the mean, sir. Third quadrant and
negative
negative
y
Y
axis.
axis, sir.
Right, 225 degrees means it is in the third
180 plus
quadrant.
45,
So
sir.
baby will be coming down away from the mean position. Now that you get it, let us do the big man's work now. This a single circle is going to prove everything. Remember the radius? How much was the radius?
Yes, sir.
A.
A.
Remember the angular velocity?
Yes, sir.
Omega.
Yes, sir.
Now let us say the particle took some time t to get there. The mummy took some time t to get there. So the angle rotated is nothing but omega t.
Yes, sir.
Yes, sir.
Now for that a, I'm going to take the projection. If this is a, this is theta, this will be a cos theta and this will be
A sin theta, sir.
a sin theta. Y equals to a sin theta. Now y equals to a sin theta. In the place of theta, I put, in the place of x, we have y now. That's all. Like we have an SHM vertically now. So we can call it as y. So how simple we have this equation already. Y equals to a sin omega t. This is the equation for the displacement of this particle. Remember how far we have to travel previously to get to this equation? Where is that torturous, monstrous equation? Yeah, we remember how far we had to go there. This is it. And the omega even makes more sense. The omega is clearly representing, for mummy, it is nothing but the angular velocity. And for baby, this is where we introduce it. For the baby, we call it as the angular frequency. Now, what does this mean? It really doesn't mean anything. There is nothing about, for the baby, which is just going in SHM, there is no such thing as angle. Like the body is not projecting any angle. The body is not going in an angular velocity. There is nothing angular about the oscillation of the SHM particle. It is just the mummy which is representing this has the same angular velocity. So that is a, what do you say, the significance of this omega. It is exactly going with the same frequency. By the time the mummy completes one full revolution, the baby completes one full oscillation. So this angular frequency is talking about the frequency of oscillations itself. So that is the importance of this thing. So that is the first step that we have, right? We take towards this whole monstrous process, but it's a lot more easier method. This is a, this is omega t. So the displacement of the particle is directly a sin omega t. That's it. Now, once we have the displacement, we basically have everything. Now, what do you want to talk about, guys? You go ahead. Like, you want to talk about speed? You want to talk about acceleration? You guys tell me and we'll talk about it. You want to talk about acceleration? You want to talk about speed?
Sir, I want to talk about velocity, sir.
What?
Velocity is same or easy, sir. Velocity.
Velocity, yeah. Let's do the velocity itself. We have
Yeah,
y equals to
let's
a
say like
sin
the
omega
baby
t.
went X distance, sir.
You do dy by dt, you get a cos omega t. Now, when I have cos omega t, I just for fun write it as 1 minus sine square omega t. Get that?
Yes, sir. Got it.
Yeah, you did
Oh,
something
wait a
different.
second. Wait a second. I forgot differentiation thing here. When I differentiate it, it's not just a cos omega t.
It's into d by dx of omega t it is.
Yeah. So when I write dy by dt, I have to leave out a. I have to write d by dt of sine omega t. When I differentiate this thing, when I get obviously get cos omega t, but I have to differentiate the inside
To
function
omega,
also. So
sir.
I get
We'll have an
additional
additional
omega.
omega.
So I get dy by dt equals to a omega cos omega t. So dy by dt equals to omega into a into root over 1 minus sine square omega t. Since you know sine theta equals to root over 1 minus cos square theta, or cos theta equals to root over 1 minus sine square theta. I'm going to send that a inside, a square minus a square sine square omega t. Now this thing is nothing but speed omega a square minus x square. We have it. So
It's also a different process, sir.
this equation is also there. This equation is clearly presenting now. We don't even have to do this also.
Yes, sir.
We don't even have to do this also. Tell me how.
Yes, sir. So, yes, sir. So, like, we know that the baby distance and that mother's distance will be is really.
You know this angular velocity, right? Can you directly not write this velocity? You do that, you will get the same thing. Again, we also did the same thing. So, but it's a lot more easier. Obviously, once you have the velocity equation, let me take a new page.
Sir,
Yeah.
it will be like plus or minus omega root a square minus x square, right?
Where do you find a plus or minus for cos?
Yes, sir.
No. Like you don't use that thing in trigonometry. When it comes to trigonometry, you can happily write cos theta equal to root over 1 minus sine square theta. You don't write plus or minus. No.
Okay.
Okay.
Yes, sir.
There is a reason that like they might teach you that, but I'm not really sure they would teach you that. In when it comes to trigonometry, you don't use that cos square theta equals to root over 1 minus sine square theta. So
Okay.
let me get to this point. Yeah, we have y equals to a sine omega t, which is very simple. V equals to a omega cos omega t, which is also very simple. I want acceleration, so I differentiate this again, dv by dt. I differentiate it again, I get a omega is a constant. I have to differentiate only the cos omega t part. I only differentiate, I have to differentiate cos omega t part. So differentiation of cos is nothing but minus sine
Minus
theta, so
sine, sir.
minus sine omega t. And differentiating the inside function gives you
So
another
additional
omega.
omega, sir.
So a omega square, the minus is here, sine omega t. Ready to be surprised? Minus omega square a sine omega t. What do we have here?
X, sir. Minus omega square x.
Yes, sir.
Right at this equation is when you just proved acceleration is proportional to minus x for that baby, which is sorry, let's put the baby in blue, or the projection, they call this as a projection. So that is why in a circular motion, the projection on y-axis is executing SHM. Okay. Now, once you have this thing, yes, somebody, Gopika is saying now we can use V equal to R omega to get the speed. Yes. That is why, like, look at this, like, try to understand as much as into this diagram that we just made, that mummy baby diagram. This is a beautiful diagram. The radius is A, it has an angular velocity omega. So the mummy always has A omega. Like when it is here, it is A omega. Since it is parallel, the baby also has A omega. That is why the baby's speed was at the mean position is A omega, if you remember that. Okay, so you can bring a lot of conclusions from this thing. Okay. Aniket, what is it? You're saying
So
something?
one small doubt,
Yeah.
in the SHM, why do we first of all need this omega square, sir? Like we can happily work with the K.
Yes, we can. But to link that is why, like, in that process, you shouldn't mention it as omega at all. You should actually work the whole thing with just k by m only. Until the point that we didn't mention that this omega is there, there is something called omega, which is linked to this thing. You shouldn't mention omega, but look at HCFM's textbook. In the first page itself, the very first page itself, this is the first page, and this is where you find a equals to minus omega square. You don't even understand why there is an omega there. So
Yes, sir.
I don't completely like the way it is introduced there. Okay, you can happily work your way around using just by k by m in the previous processes. But right now we just came up with a very interesting process. It is there in HCFM. They mentioned this process also. Okay, but they didn't highlight this. I want to highlight this process, which is a much easier process when it comes to solving problems, when it comes to especially times taken. We will play with all those times and all other problems tomorrow, but for now, try to clearly observe one thing. When mummy goes by angle 30 degrees, this is a sine 30, so it goes to plus a by 2. When mom goes to 45 degrees, the baby goes to plus a by root 2. And mom goes to 60 degrees,
Sir,
the
A by
baby,
row 2, sir.
yeah, a by root 2 plus root 3 a by 2. And 90 degrees, it's plus a. Again, 150 degrees, oh, sorry, 120 degrees, 135 degrees, 150 degrees, 180 degrees, 210 degrees, 225 degrees, to wait a second, to
So
40
240,
degrees,
sir.
to 70 degrees, to 300 degrees, 335. Anybody? No, this is not 335, I guess. This is 300. uh, did I miss something? This is 360, right? So this is 330. Yeah, it is 315. I'm sorry. So guys, remember all these values, all these values that I just put on, they're all important. And all you need to remember is these three values only. Like it repeats, counts constantly. Let me draw a neat, clearer diagram. I don't think I need to. Let's do it. Okay, let's be professionals. Let me take that other app so that it is very easy to draw a circle. Where is that other notes app? Yep, it is here. So no, I want a circle. Yep, finally. Yeah, better. So all the angles I'm mentioning again: 30 degrees, 45 degrees, 60 degrees, 90 degrees, 120 degrees, 135 degrees, 150, 180, 210, 225, 240, 270, 300, 315, 330, 360, or which is also 0. So all these values must be remembered. So that these values again, like plus a by 2, plus a by root 2, plus root 3 a by 2, minus a by 2, minus a by root 2, minus root 3 a by 2. Try to remember all these values, guys. Like it is easier for you people to just remember these values, because whenever they ask you some values, like immediately ask you, it gets a lot more easier for you to just give the value. Somebody raise a hand. What is it?
Yes, sir.
Yeah,
Sir, once can you show one problem with this, sir? I can't understand how it will be useful.
yeah. Let us say they simply ask you the particle traveled from mean to plus a by root 2. Mean
Okay,
to plus
sir.
a by root 2. Okay. What is the time taken? Instead of writing the whole equation, look at the mummy. The mummy simply traveled 45 degrees. For the
Oh,
mummy to fully complete 360 degrees, what is the time taken? One time period. But to complete 45 degrees, which is 1/8 of this whole motion, so it only takes t by 8. So
okay, sir.
without even looking at the problem, without even solving this part, just by looking at the corresponding mummy, you can give all the time periods, all the values, whatever the value that you want, you can happily give. We will play with these values tomorrow. I'm telling you, we will definitely play with these values tomorrow. But for today, just look at this diagram as much as you can. Try to remember all the values. Tomorrow, I'm going to simply ask you like, baby is at plus a by root 2. Baby is at plus a by root 2 going towards the mean position. What is the angle, Aniket?
45.
No, you're being stupid. Plus a by root 2 going towards the mean. Let me show you.
135, sir.
It is here going towards the mean. So it must be 135 degrees. The mummy must be at 135 degrees. So I give you all these things like I say the baby is at minus a by 2 going towards the mean position. Can anybody give me the answer?
Sir, 330, sir.
Exactly. The mummy will be at 330 degrees. So I'm going to ask you these questions tomorrow. Like directly, I give you a position, mummy's position or baby's position. I'll give you the angle, ask you the baby's position. I'll give you the baby's position, ask you the mummy's angle. You need to prepare these angles. Like you need to run some complete simulation in your minds. Like you should be ready to give you any answer at any point. If you're ready to do that, trust me, tomorrow's topic gets a lot more easier. Okay. Just for fun, I'm not putting any pressure today. Just for fun, go out there into the exercises and start doing the questions. You might find one or two questions difficult, but trust me, you will get some insight into the problem. So, come on. It's a long topic. So, yeah, buckle up. So all these problems, just try to give them a try. Exercise up to 1 to 7, 8, 9. You can try some questions. Okay, you try some questions, give them some effort, put some effort into it. There is a chance that you might get it. If you don't get it, it's totally fine. Okay, by tomorrow you will get a complete idea. Once you have the complete structure of this, you will completely have a very good idea by tomorrow. All right. Anything else before I end the class? It's a very long class today. It's almost what, 1 hour, 10 minutes. So thanks so much. I think I took way too long already. So we'll meet again tomorrow in the same class. Come prepared with those values. We'll be happy doing it all. All right.
Thank you,
Thanks
sir.
so much.
Thank you, sir.
Bye bye.